For more than 30 years, astronomers have been finding giant planets around other stars, and almost every single one of them has fallen into one of two extremes. Either they orbit so close to their star that surface temperatures reach thousands of degrees, or they sit so far out that they're frozen solid, hundreds of degrees below zero. In May of this year, NASA confirmed something genuinely different: a giant planet roughly the size of Saturn, sitting comfortably in between those two extremes, with a temperature mild enough to compare to the inside of a parked car sitting in the sun. Researchers had predicted a planet like this should theoretically exist. They just hadn't ever actually gotten a detailed look at one before. This is the real story of TOI 199b, why astronomers are calling it one of the first true temperate giant planets ever studied in detail, and why finding methane in its atmosphere has scientists genuinely excited about what it could teach us, not just about distant gas giants, but about how planetary atmospheres, including our own, actually form and evolve. If you want real discoveries explained accurately instead of exaggeration, subscribe now, because this specific planet is about to become a major target for follow-up research. It's worth understanding why this particular detection required Webb specifically, rather than any earlier generation of space telescope, because the technical demands involved are genuinely significant. Methane's specific absorption signature sits in the infrared portion of the light spectrum, exactly the range Webb's instruments were purpose-built to detect with extraordinary sensitivity. Earlier space telescopes, including Hubble, simply weren't equipped with the same level of infrared sensitivity or spectral resolution needed to reliably tease apart a specific molecule's faint signature from the overall combined light of a star and its transiting planet, particularly for a planet as comparatively far from its star, and therefore comparatively infrequent in its transits, as TOI 199b. Webb's combination of a much larger primary mirror and instruments specifically tuned to infrared wavelengths gave researchers a level of precision that simply wasn't available to the field before this specific telescope became operational, which is a significant part of why detailed atmospheric characterization of a genuinely rare planet type like this one had to wait until now to actually happen. Let's start with why this particular temperature range is such a big deal in exoplanet science, because it isn't simply a matter of one planet being slightly warmer or cooler than another. Since the first exoplanet orbiting a sun-like star was confirmed back in 1992, astronomers have identified thousands of worlds beyond our own solar system, and the giant planets among them have overwhelmingly clustered into two familiar categories. The first category is what astronomers call hot Jupiters, giant planets that orbit extremely close to their host stars, often completing a full orbit in just a few days and reaching blistering temperatures of thousands of degrees as a direct result of that close proximity. The second category looks more like the gas giants in our own solar system, Jupiter and Saturn, sitting far enough from the sun that they remain extremely cold, hundreds of degrees below zero, essentially frozen worlds shaped by their enormous distance from any meaningful source of heat. Renyu Hu, an associate professor of astronomy and astrophysics at Penn State's Eberly College of Science, and the researcher who led the team responsible for this discovery, explained exactly why that gap between the two extremes matters so much scientifically. One of the biggest advantages of studying exoplanets, he noted, is the opportunity to examine many different types of planets, especially the kinds we simply don't have anywhere in our own solar system, in order to understand how planetary systems actually form and evolve more broadly. Astronomers have found thousands of exoplanets since 1992. Hugh pointed out, but only a small handful of known giant planets actually fall into this specific temperate category, sitting genuinely in between the blazing hot and the frozen extremes most giant exoplanets occupy. And until this particular study, none of those rare temperate giants had ever had their atmosphere studied in this kind of detail. If a story built on real peer-reviewed research published straight from the scientists who made the discovery is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. TOI 199b itself orbits a star located more than 330 light-years from Earth, completing one full orbit roughly every 100 days, a genuinely leisurely pace compared to the tight, blisteringly fast orbits typical of hot Jupiters. That relatively distant, comparatively slow orbit is exactly what gives the planet its mild temperature, estimated at around 175 degrees Fahrenheit. That's still extremely hot by the standards of everyday human experience, roughly comparable to the inside of a car left parked in direct sunlight on a hot day. But it represents a dramatic departure from the thousands of degrees typical of a hot Jupiter, while remaining considerably warmer than the deeply frozen gas giants found throughout our own solar system. In effect, TOI 199b occupies a genuinely rare middle ground, a giant planet mild enough that its atmosphere behaves in ways scientists had really only been able to theorize about before now. It also helps to understand exactly what Saturn-sized actually means in this specific context, because the comparison to our own solar system's second largest planet is doing real, meaningful work in helping picture what TOI 199b is actually like. Saturn itself is a genuine giant among planets, more than 9 times wider than Earth, composed overwhelmingly of hydrogen and helium gas, rather than any kind of solid, rocky surface a spacecraft could ever land on. TOI 199b shares that same basic gas giant structure and roughly comparable overall size, but where Saturn sits nearly 900 million miles from our own sun, cold enough that its cloud top temperatures plunge to roughly minus 220 degrees Fahrenheit. TOI 199b's own orbit leaves it running around 175 degrees Fahrenheit instead, a temperature difference of nearly 400 degrees between two planets that are otherwise, in terms of raw size and basic composition, genuinely comparable to one another. That stark contrast is exactly what makes TOI 199b such a valuable natural laboratory, a chance to study essentially a Saturn-like world running at a dramatically different, considerably milder temperature than anything found in our own solar system, letting researchers isolate exactly how temperature alone reshapes a giant planet's atmospheric chemistry, independent of the other variables that would normally complicate such a comparison. To actually study that atmosphere in detail, researchers turn to a technique called transmission spectroscopy, a method that relies on watching a planet pass directly in front of its host star from our vantage point here on Earth. As Aaron Bello-Aruf, a postdoctoral researcher at NASA's Jet Propulsion Laboratory and the study's first author, explained, as a planet transits across its star, some of that starlight passes directly through the planet's own atmosphere on its way to our telescopes, interacting with whatever elements and molecules happen to be present there. It's also worth acknowledging where TOI 199b's own designation actually comes from, because the planet wasn't discovered by Webb in the first place. The TOI prefix stands for Test Object of Interest, indicating the planet was originally flagged as a promising candidate by NASA's Transiting Exoplanet Survey satellite, a dedicated planet-hunting mission that scans large swaths of sky, specifically looking for the telltale dimming pattern produced when a planet transits in front of its star. TESS was never designed to study a planet's atmosphere in any real detail. Its job is simply to find promising candidates and measure basic characteristics like orbital period and rough size, flagging genuinely interesting targets for follow-up study by more specialized instruments. TOI 199b represents exactly that kind of successful handoff. An initial detection by a wide-field survey telescope, followed by genuinely detailed atmospheric characterization from Webb, the same basic two-step discovery process, responsible for a considerable portion of Webb's most significant exoplanet results to date. The actual observation campaign behind this discovery required a genuinely significant investment of Webb's extremely limited and heavily competed for observing time. Researchers first gathered roughly 20 continuous hours of observations simply to establish an accurate baseline measurement of the host star's light on its own, uninterrupted by any planetary transit. The actual transit of TOI 199b across its star lasted around 7 hours, considerably longer than the transits typically observed for hot Jupiters, which can last an hour or less, given how tightly and quickly those planets orbit their stars. Once that transit data was gathered, researchers compared the light spectrum recorded during the actual transit against the earlier baseline measurement, and the differences between the two revealed exactly which wavelengths of starlight had been absorbed by the planet's atmosphere on its way through, allowing the team to identify the specific gases responsible. There's a deeper reason that methane specifically makes such a valuable tracer molecule for understanding a planet's broader atmospheric chemistry, beyond simply being one gas among several worth detecting. In giant planet atmospheres, the balance between methane and other carbon-bearing molecules, particularly carbon monoxide, is highly sensitive to a planet's internal temperature and the way gases mix vertically between a planet's deeper, hotter layers and its cooler upper atmosphere. Confirming methane as the dominant carbon-bearing gas in TOI 199b's atmosphere, rather than carbon monoxide, gives researchers a genuinely useful clue about the underlying thermal and chemical structure of the planet's deeper atmosphere, information that would be difficult to obtain through any other means for a planet this far away. What they found, according to Bello-Aruf, was that the atmosphere blocked precisely the wavelengths of starlight known to be absorbed by methane. That detection carried real scientific weight beyond simply adding one more molecule to a checklist. Existing theoretical models, predicting the likely composition of temperate gas giant exoplanets, had specifically predicted that methane should be present in an atmosphere like this one. And confirming that prediction against real, direct observational data represented a genuine validation of those underlying theoretical models, the kind of direct confirmation that simply hadn't been available before Webb's instruments made this level of detailed atmospheric analysis possible. Beyond the confirmed methane detection, the same observations also turned up hints of two additional gases, ammonia and carbon dioxide, though researchers noted that confirming those specific detections with full confidence would require additional follow-up observations beyond what this first study alone could establish. Hu was direct about why nailing down the complete atmospheric composition of a planet like TOI I-199b actually matters for science well beyond this single distant world. With additional observations, he explained, researchers could establish the relative abundance of each of these various gases within the planet's atmosphere, building a genuinely complete picture of what a temperate gas giant's atmosphere actually looks like in detail. That complete picture, in turn, could then be used to refine and improve existing models of how planets and their atmospheres form and evolve more broadly, including, potentially, offering new insight into the history of Earth's own atmosphere. That's a genuinely significant claim worth sitting with. A planet more than 330 light-years away, a giant world with no rocky surface and no realistic chance of ever hosting anything resembling life, could still end up teaching scientists something meaningful about the history of the one planet we actually call home. I think simply because studying how atmospheres behave across a wide range of different planetary conditions helps researchers build more accurate, more broadly applicable models of atmospheric chemistry and evolution in general. It's worth understanding why finding and studying a planet in this specific temperature range has proven so difficult for astronomers up until now, because the challenge isn't simply that temperate giant planets are rare. Planets that orbit relatively far from their host stars, the same distance required to produce a mild, temperate climate rather than a scorching hot Jupiter's blistering heat, also tend to produce comparatively weak, harder to detect transit signals, since a more distant orbit generally means a planet blocks a smaller fraction of its star's overall light during each individual transit, and transits themselves happen less frequently given the longer orbital period involved. Hot Jupiters, by contrast, transit frequently and produce strong, easily repeatable signals precisely because they orbit so closely and so quickly, which is part of why they became the dominant, most thoroughly studied category of giant exoplanet in the field's earlier years. Essentially because they were the easiest kind of giant planet to actually find and confirm using the transit method in the first place. TOI 199b's own 100-day orbital period meant researchers had comparatively few opportunities to actually catch it transiting at all, making this specific successful observation campaign considerably harder to pull off logistically than a comparable study of any typical hot Jupiter would have been. There's also a broader significance to this discovery worth understanding within the context of exoplanet, science's own historical development as a field. Hu specifically noted that the first exoplanet ever discovered orbiting a sun-like star was found back in 1992 by a research team that included Alexander Wolszczan, himself a researcher at Penn State, the same institution now leading this current study more than 3 decades later. That's a meaningful piece of context, because it places TOI 199b's discovery within a direct, continuous scientific lineage stretching back to the very earliest confirmed exoplanet detections, a field that's grown from a single, groundbreaking discovery in the early 1990s into a research area now capable of directly analyzing the detailed atmospheric chemistry of a giant planet orbiting a star more than 300 light-years away. Hu was also candid about exactly where this research goes from here, framing this initial study as a genuine starting point rather than a finished, complete picture. The success of this first detailed study of a temperate giant planet's atmosphere, he explained, gives researchers real confidence to dedicate additional resources and observing time towards studying other similar planets going forward. The core question driving that continued research is a genuinely open one. Whether TOI 199b represents some kind of unique, unusual outlier among temperate giant planets, or whether it actually shares general, common characteristics with other planets of this same broad type that simply haven't been studied in this kind of detail yet. Answering that question properly requires exactly the kind of expanded observational campaign Hu described, applying the same transmission spectroscopy technique used here to additional temperate giant planets as they're identified, building up a genuine comparative dataset, rather than relying on a single, isolated example. Looking beyond Webb specifically, this discovery also arrives at a moment when the broader field of exoplanet atmospheric science is actively expanding its available toolkit. The European Space Agency's Ariel mission, currently in development and expected to launch before the end of this decade, is being specifically designed to survey the atmospheres of roughly 1,000 exoplanets in a systematic, large-scale way, rather than the deep, resource-intensive study of individual targets that missions like Webb currently specialize in. A discovery like TOI 199b's confirmed methane atmosphere serves as exactly the kind of proof-of-concept result that helps justify and shape those future, larger-scale survey efforts, demonstrating precisely what kind of detailed chemical information is achievable for a temperate giant planet, and helping researchers prioritize which additional targets among the thousands of already cataloged exoplanets are most likely to reward the same kind of detailed atmospheric follow-up once more observing capacity becomes available. It's worth being clear about the scale of collaboration this specific study required too, because a result this detailed rarely comes from a small, isolated team working alone. The research published in the Astronomical Journal in May of this year involved contributors not just from Penn State and NASA's Jet Propulsion Laboratory, but also from Arizona State University, Johns Hopkins University, the Carnegie Institution for Science, the California Institute of Technology, and the University of California, Santa Cruz, a genuinely broad, multi-institutional collaboration reflecting how specialized modern exoplanet atmospheric research has actually become, requiring expertise spanning observational astronomy, atmospheric chemistry modeling, and detailed spectral analysis, all working together on a single shared dataset. It's worth understanding a bit more about the star TOI 199b actually orbits too, because the planet's temperate classification only really makes sense in the context of the specific star providing its heat. Unlike the extremely hot, luminous stars that many known hot Jupiters orbit, where even a comparatively distant orbit can still leave a planet blisteringly hot, TOI 199b's own mild temperature emerges from a specific combination of its host star's characteristics and its own 100-day orbital distance, striking a genuine balance that neither cooks the planet the way a tighter orbit would, nor freezes it solid the way a considerably wider orbit around the same star eventually would. That balance is precisely what makes systems like this one comparatively rare finds, requiring survey missions like TESS to catch a specific, fairly narrow combination of orbital distance and stellar brightness in order to flag a genuinely temperate giant planet candidate worth Webb's considerably more limited and valuable follow-up observing time in the first place. There's one final detail worth including, because it speaks to just how quickly this specific corner of exoplanet science is likely to develop from here. Hugh's own team has already signaled that additional temperate giant planet candidates are being actively considered for future Webb observing proposals, meaning the single data point represented by TOI 199b is likely to gain genuine company within the next few years rather than remaining an isolated curiosity. Whether those future targets confirm methane as a consistently dominant atmospheric gas across this entire planetary category, or instead reveal genuine diversity from one temperate giant to the next, remains an open question that only continued observation can actually answer. And it's exactly the kind of open question that tends to keep a specific area of astronomy exciting for years after the first foundational discovery gets made. So, what does all of this actually add up to? NASA confirmed that the James Webb Space Telescope had successfully studied the atmosphere of TOI 199b, a Saturn-sized giant planet orbiting a star more than 330 light-years away, finding it to be genuinely rich in methane, exactly as theoretical models had predicted, while also turning up promising hints of ammonia and carbon dioxide, worth confirming through future observations. What makes this discovery genuinely exciting to the scientists involved isn't a single dramatic headline moment, but the fact that TOI 199b represents one of the very first detailed atmospheric studies ever conducted of a genuinely rare category of giant planet, a world sitting in the mild, temperate middle ground between blazing hot Jupiters and the frozen gas giants found throughout our own solar system. There's a specific kind of scientific excitement running through this entire story that's worth naming directly, because it's genuinely different from the excitement surrounding a single, unrepeatable, headline-grabbing anomaly. This is the excitement of watching a theoretical prediction, built up over years of modeling work, get tested directly against real data for the first time and hold up. That's a quieter kind of thrill than discovering something nobody expected at all. But it's arguably just as important to the actual progress of science, confirming that the underlying physics and chemistry researchers have been relying on to understand planets they can't directly visit actually describes reality accurately, at least for this one genuinely rare category of world. If stories like this, grounded entirely in real, published research instead of exaggerated headlines, are what you come here for, subscribe to this channel and turn on notifications, because Webb's exoplanet research program is only expanding from here. And there's a very real chance the next temperate giant planet discovered adds even more detail to exactly this story. Thanks for watching, and I'll see you in the next one.